I was just thinking about your typical Tuesday morning. You're a security professional. You've got your coffee. You're sitting there staring at your dashboard.
Right, just bracing for the day.
Exactly. You are dealing with the daily grind. You're deploying cloud infrastructure. You're triaging this absolute mountain of alerts, and you're constantly fighting to keep that attack surface as small as humanly possible.
It's exhausting.
It really is. And amidst all that noise, right, the Jira tickets, the Slack pings from developers that never stop,
Yeah.
there is this silent threat just growing in the background of your environment.
Yeah, the stuff nobody wants to look at.
Exactly.
Yeah.
We were talking about cloud VM sprawl and zombie resources. It is this hidden, quiet mess that it isn't just burning through your IT budget at an alarming rate, but it's actually actively, systematically opening back doors into your carefully guarded cloud environment.
It's the ultimate blind spot. You simply cannot secure an asset if your asset inventory doesn't even acknowledge its existence. Spot on. So before we get into the weeds, welcome to InfoSec Bytes, your go-to podcast for bite-sized insights on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis. With over 100 episodes, we've got you covered on the latest trends and tips. This year, we will focus more on cloud computing along with other topics, so stay tuned. Please like, subscribe, and share to join the conversation on various platforms: Spotify, Apple Podcasts, YouTube, Amazon Music, and stay secure.
Awesome. So if we really want to tear down why our cloud environments are currently bleeding money and, generating these critical vulnerabilities, we have to start by looking at the architecture of resource entropy.
Resource entropy, I like that.
Yeah, we basically have to look at how the transition from physical infrastructure to the cloud created this proliferation paradox.
The proliferation paradox. I love that term because it perfectly encapsulates the irony of where we are right now, right?
Oh, 100%. To really grasp it, we need to contrast the current state of affairs with how things operated, say, 15 or 20 years ago in the bare metal era.
Right, back when servers were heavy.
Exactly. Because back then, the friction was the security policy. Think about what the typical procurement cycle looked like for a systems admin who just wanted to rack a single database server.
It was an absolute gauntlet. You couldn't just have an idea on a Tuesday and build it on a Wednesday. The process basically forced you to justify the existence of that server.
Right. You started by writing this massive business justification document. And then that went to a management committee.
And then it went to finance.
Oh, yeah, the finance committee, to get your capital expenditure, your CapEx budget approvals. And once the money was finally released, you had to negotiate with hardware vendors, deal with the supply chain logistics, and then wait, 4 to 6 weeks for a physical box to actually show up at the loading dock?
If you were lucky.
Right. And then the actual manual labor begins. Someone is physically unboxing this thing, mounting it on sliding rails in a server rack, running the redundant power supplies, punching down the CT6 Ethernet cables.
Whole 9 yards.
Yeah. Then you're doing a network boot. You're manually installing a Linux or Windows OS and painstakingly configuring the firewalls.
And that entire agonizing process, the sheer pain and cost of it, it acted as this incredible natural governance mechanism.
Right.
You did not provision a physical server unless the business absolutely undeniably required it. So the environment stayed relatively clean because adding clutter was simply too difficult.
But then we get the virtualization revolution. And just as a quick level set for anyone who might not be living in the infrastructure weeds every day, when we talk about virtualization, we're really talking about the introduction of the hypervisor.
Yep, the abstraction layer.
Exactly. This is that software abstraction layer, think VMware, ESS, Microsoft Hyper-V, or KVM, that sits directly on the bare metal physical hardware. It takes those physical CPUs, the RAM, the spinning disks, and partitions them into isolated virtual environments.
Right. And that decoupling of the operating system from the physical hardware, it changed everything regarding utilization.
How so?
Well, in the pure bare metal days, you might have this massive, expensive server running a single application, and it's sitting at maybe 5 to 15% CPU utilization.
Wow. So just wasting all that power.
Massive waste of physical resources. But the hypervisor allowed us to stack 20, 30, or 40 virtual machines onto that single physical box, which pushed aggregate utilization up to 80% or more.
So it's a massive leap forward. But the real paradigm shift, the catalyst for the sprawl we see today, wasn't just virtualization. It was cloud-native virtualization.
Exactly. AWS, Azure, GCP.
Right. They took that virtualization layer, and slapped a globally accessible, authenticated API right in front of it.
Yeah.
We went from a 6-week multi-department procurement cycle to like a 6-second API call.
It's wild when you think about it.
It is. A junior developer can now write a single line of Terraform code and spin up a globally distributed load-balanced cluster of 64 core virtual machines, just like that.
Which brings us directly to the proliferation paradox itself. The exact technology that was engineered to maximize computational efficiency, the frictionless, API-driven provisioning model of the public cloud FLID, it has become the primary engine of digital waste.
Right, because we just can't keep up.
Exactly. Our ability to create resources has exponentially outpaced our organizational ability to govern, track, and eventually decommission those resources.
And that unchecked creation, it leads to a very tangible mathematical problem on the underlying hardware. Let's dig into the research on the concept of synthetic saturation.
Oh, this is a huge one.
Because I think a lot of people assume that if a virtual machine is just sitting there doing absolutely nothing, if it's a true zombie, it isn't impacting the rest of the environment. But that's a dangerous misconception, isn't it?
It's a huge misconception, yeah. To understand synthetic saturation, you have to look at how a physical host server actually calculates its total utilization.
Okay, break that down for me.
So that total utilization isn't just the sum of the active workloads. It's an equation with 3 variables. First, you have the actual productive work being executed by the active VMs.
Makes sense.
Second, you have the memory and compute resources that are formerly reserved by those idle zombie VMs, and those are locked away and inaccessible to other workloads, even if they're currently unused.
So they're just holding on to it.
Exactly. And third, you have the hypervisor's own management overhead.
Let's focus on that third variable for a second, the hypervisor overhead. Because the hypervisor isn't just this magical zero-cost entity, right? It's an operating system in its own right, and it requires CPU cycles to actually function.
Precisely. Every single virtual machine you provision, regardless of whether it's processing millions of transactions or sitting entirely dormant, it demands constant attention from the hypervisor.
Like what kind of attention?
Well, the hypervisor has to manage memory address mappings for that VM. It has to handle interrupt requests. It's constantly running heartbeat monitoring to ensure the guest operating system hasn't panicked or locked up.
Okay, I see where this is going.
So as you let these idle, forgotten zombie VMs just pile up in your cloud environment, that baseline hypervisor management overhead grows steadily.
Which inevitably creates a noisy neighbor scenario.
Right.
The hypervisor is burning so many CPU cycles, just managing the administrative existence of hundreds of useless zombies, that it starts starving the legitimate active workloads.
Exactly. And the metrics will show that the physical host is mathematically saturated, like it's running at 95% capacity, but the actual productive revenue-generating output of that server is dismal.
So that is synthetic saturation in a nutshell.
Yep. And it forces the cloud infrastructure team into a terrible corner because their monitoring tools are screaming that the cluster is out of resources.
Right, the alarms are going off.
So the automatic response is to provision more hardware or spin up larger instance types to handle the load. You end up buying more capacity just to mask the fact that you are drowning in your own unmanaged waste.
Wow. Okay, so we understand the mechanical failure, but I want to pivot to the human element for a second, the psychology of the engineering teams building this stuff.
Oh, this is where it gets really interesting.
Right, because no cloud architect or DevOps engineer wakes up in the morning, logs into the AWS console, and thinks, I'm going to waste $20,000 of my company's money today.
Definitely not.
But there is this deeply ingrained, almost institutionalized just-in-case over-provisioning mindset.
It all comes down to fear and incentive structures, really. Developers and site reliability engineers, they are evaluated on uptime and performance. They are absolutely terrified of bottlenecks. If an application falls over because it hits a memory limit during a traffic spike, that engineer is the one whose pager goes off at 2 a.m. on a Sunday.
Ugh, the dreaded 2 a.m. page. So, to protect their sleep schedule and their performance reviews, they overcompensate.
Yeah.
They look at a microservice that historically peaks at maybe 4 vCPUs and 16 gigabytes of RAM, and they think, you know what? Let's provision an instance with 16 vCPUs and 64 gigs of RAM, just to be absolutely safe.
And because the cloud has removed all the friction, there's no one to stop them. There's no physical hardware limitation. There's no procurement committee reviewing the request.
Just click a button.
Or they just change a variable in their infrastructure as code repository. Merge the pull request, and the cloud provider happily fulfills the order.
But wait, let me play devil's advocate here.
Yeah.
If we look at the core value proposition of the cloud, isn't agility the entire point? Like, we migrated away from on-premise data centers specifically so our engineering teams could move fast, iterate quickly, and deploy without all those bureaucratic roadblocks. If we start adding friction back into the provisioning process, if we make them jump through hoops just to get a testing environment, aren't we just dragging ourselves back to the dark ages of IT?
That's a really common pushback from development teams, but it conflates two very different concepts.
Okay, what are they?
Agility is the capability to move quickly and adapt to market demands. Negligence is failing to maintain the environment you are moving quickly within.
I like that distinction.
We want developers to be able to spin up 50 servers in 5 minutes to test a new feature. That's great. The problem is what happens after the test is over.
I think the best way to visualize this is to compare a multi-cloud environment to a massive modern self-storage facility.
Okay, yeah.
The beauty of this facility is that renting a unit is frictionless. You just swipe your corporate badge, the door opens, and you have an empty unit to store whatever you need for a quick project. Teams are grabbing units left and right for development, staging, QA, proofs of concept.
Right, the frictionlessness is a feature, not a bug.
Exactly. But the breakdown happens on the exit.
Oh, yeah. Nobody cleans it out.
Exactly. The problem isn't that renting the storage unit is easy. The problem is that nobody ever goes back to empty it. The engineer finishes the proof of concept, they move on to the next sprint, and they leave the storage unit completely full of digital junk.
Yeah.
And because the company has a centralized billing account, it just quietly continues to pay the monthly rent on hundreds or thousands of these forgotten, locked units for years on end.
And that brings up the critical issue of lifecycle management. A resource should never, ever be created without a predefined plan for its destruction.
I want to pause for a second. If you are listening to this right now on your commute or sitting at your desk, think about your own primary cloud account. Think about your AWS organization or your Azure subscriptions.
Be honest with yourself.
Seriously, how many instances were spun up for a quick 2-week proof of concept 3 months ago by an engineer who has since transferred to a completely different department? And those instances are still running right now.
If you actually go in and run the queries, the answer is going to terrify you.
Absolutely.
And that financial bleed is exactly what drives the next logical question, right? If we are wasting this much money, what else are we exposing? But before we get to the security implications, we really have to build the business case.
Because money talks.
Exactly. If you want your C-suite or your board of directors to prioritize a massive cleanup effort, you have to show them the financial hemorrhage first.
And the numbers from the research are just absolutely staggering. Gartner estimates that 30 to 35% of enterprise cloud budgets are wasted annually.
30 to 35%.
Specifically, this waste is attributed to unused virtual machines, orphaned resources, and duplicate forgotten environments.
Let's put that into perspective for a second. If you are a mid-sized enterprise with an annual cloud spend of, say, $10 million, you are literally setting $3.5 million on fire every single year.
Just burning it.
That's not money spent inefficiently. That is money spent on infrastructure that is doing zero compute work for your business.
So to really attack that waste, we need to understand the taxonomy of these zombie resources. Because they don't all look the same, right?
No, they take a few different shapes.
The research generally categorizes them into 2 distinct buckets: compute zombies and storage zombies.
Let's break down compute zombies first, because these are usually the most visible. You have your classic idle virtual machines, your EC2 instances in AWS or compute engine VMs in GCP that are sitting at less than 1% CPU utilization for weeks or months at a time.
Right, the classic zombie.
But it gets way more complex than just simple VMs. We see massive waste in abandoned Kubernetes clusters.
Oh, those are expensive.
Very. A dev team will spin up an entire EKS or AKS cluster to test a new containerized microservice architecture. When they are done, they might delete the application pods, but they forget to tear down the underlying worker nodes and the control plane.
Wow. So they just leave the engine running.
Exactly. Those nodes just sit there, pulling the empty control plane, billing you by the hour.
And then you have orphan load balancers, application load balancers, or network load balancers that were provisioned to route traffic to a back-end target group.
Right.
The target group gets decommissioned, the back-end servers are deleted, but the load balancer itself is left running, completely disconnected from any back-end logic, just waiting for internet traffic that will never be served.
And it still costs money. So that covers the compute side, but storage zombies are often far more insidious.
Really? Why is that?
Because compute costs are usually high enough that they eventually trigger an alert. Storage feels incredibly cheap, it's just pennies per gigabyte until you aggregate it across an entire enterprise.
Ugh. Death by 1,000 cuts. And storage zombies take several forms, don't they? The classic example in AWS is the unattached elastic block store, or EBS, volume.
That's a huge one.
An engineer goes into the console to terminate an EC2 instance. They click terminate, the compute instance dies, and the hourly compute billing stops. But they didn't check the little box that says delete on termination for the attached hard drive.
Happens all the time.
So the compute is gone, but the 500 gigabyte SSD volume detaches and just sits there in the account, quietly billing you every single month.
And another massive contributor to storage waste is stale snapshots. Taking an automated snapshot of a virtual machine's disk before executing a major software upgrade or a patching cycle, that is an incredibly sound engineering practice.
Right, you want a backup.
Exactly. But the issue is retention. We audit environments and we find tens of thousands of snapshots that are 3, 4, even 5 years old.
Which is completely illogical. You are never, under any circumstances, going to roll back a production database server to a state it was in 3 years ago. The data delta would be catastrophic.
It would ruin the business.
It is entirely useless data hoarding.
And don't forget about object storage mismanagement. You have petabytes of data sitting in hot storage tiers like S3 standard that hasn't been accessed by an application or a user in over a year.
Oh, that's painful.
That data should have been transitioned via lifecycle policies to a cold archive tier like S3 Glacier Deep Archive, where the storage cost is literally a fraction of a cent.
There was a really illuminating case study in the research that brings all this financial pain to life. It involves a global SaaS company that was experiencing phenomenal explosive growth.
Right, I remember this one.
They were expanding their infrastructure footprint across North America, Europe, and the Asia-Pacific regions. Revenue was climbing, but their cloud infrastructure invoices were spiraling out of control even faster than their revenue.
Yeah, and when they finally brought in external consultants to audit the environment, what they found under the hood was just a textbook case of resource entropy.
What did they find?
They discovered that 25% of their total monthly cloud spend was tied directly to idle zombie resources.
A quarter of their massive bill was pure waste. But the operational realities behind that number are what I find so fascinating. They found that over 40% of all their cloud resources completely lacked basic ownership tagging.
Nothing. No tags at all.
There was no owner tag, no cost center tag, no application tag.
Which creates a total paralysis in the engineering culture.
How so?
Well, when the FinOps and finance teams went to the developers and said, hey, we have all these untagged idle servers running in the QA accounts, we need to shut them down, the developers vehemently pushed back.
Because they were terrified. When you don't have tags, and you don't know what a server's function is or who built it, shutting it off is a massive risk. The developers literally feared that if they pulled the plug on these mysterious undocumented environments, they might accidentally sever a critical back-end dependency and cause a cascading outage in their production environment.
And that fear is the ultimate symptom of a sprawling architecture. When the environment is so messy that you are too scared to clean it, the sprawl becomes permanent.
Wow.
And we should probably take a moment to differentiate how this financial pain manifests depending on your underlying infrastructure model, because public cloud sprawl behaves very differently from private cloud sprawl.
That's a really great distinction. Let's look at the public cloud first. If you are operating entirely in AWS, Azure, or GCP, sprawl is a direct OpEx problem. It is an operational expenditure bleed.
Right, it's cash out the door.
It results in immediate bill shock.
Yep.
You get your invoice on the first of the month, and it is $50,000 or $100,000 higher than finance forecasted, simply because resources are billed by the minute or the second. It's a direct, visible cash hemorrhage.
But private cloud sprawl is far more deceptive. If you are running an on-premise VMware or hyper-converged infrastructure environment, you don't get a monthly bill for compute time. You already purchased the physical hardware.
Right.
So the sprawl represents CapEx waste, capital expenditure waste.
Yeah.
And the primary symptom isn't a surprise invoice, it is resource starvation.
Right, because those zombie virtual machines are sitting there consuming all of your available memory and CPU cycles.
Yep.
Your hypervisor clusters hit capacity.
Yep.
So when an engineering team comes to IT and says, we have a critical new machine learning project, we need 20 new high-performance VMs, the IT director looks at the vCenter dashboard, sees that the cluster is 95% full, and says, we don't have the capacity. We need to issue a purchase order for a new $500,000 storage array and 3 new physical host servers.
It's crazy. You end up going through a massive capital expenditure procurement cycle, buying brand new, expensive physical hardware, simply because your organization is hoarding digital junk on the hardware you already own. You are physically expanding the footprint to accommodate the waste.
And this precise friction between finance, IT, and engineering is what has driven the explosive rise of the FinOps movement.
Absolutely.
For anyone who might not be deep in the cloud cost management world, FinOps is essentially the practice of bringing financial accountability to the variable consumption-based spend model of the cloud. It's about breaking down the silos so that engineering, finance, and business leadership actually collaborate on data-driven spending decisions.
But FinOps is about more than just playing accountant. It is a strategic effort to reduce technical debt.
Explain that connection.
Every single zombie resource, every untagged test server is a piece of technical debt that your security and operations teams have to mentally track and account for. By aggressively clearing out that sprawl, you aren't just freeing up budget capital, you are freeing up human cognitive capital.
That's a great way to phrase it.
You're letting your engineers focus on actual innovation instead of managing a graveyard of forgotten instances.
That transitions us perfectly to the core of this deep dive. We've established the financial bleeding. You can take those Gartner numbers and that sauce case study to your CFO and instantly get their attention.
Oh, yeah.
But let's pivot to what you, the security professional listening to this, actually lose sleep over, the threat landscape. Because a zombie VM isn't just burning corporate cash. It is an unmonitored, unpatched door you have left wide open to the public internet.
This is where digital waste transforms into a weapon. The Cloud Security Alliance released a massive survey in 2024, polling thousands of enterprise security professionals, and what ranked as the absolute top threats in cloud computing.
Let me guess, not 0 days.
Nope. It wasn't sophisticated zero-day exploits or state-sponsored advanced persistent threats. The top threats were misconfigurations and IAM identity and access management weaknesses.
Which makes perfect sense when you think about the lifecycle of a forgotten virtual machine. Imagine a developer spins up an Ubuntu server in a dev account to test a new application build. They use it for a week, they finish their testing, and then they get pulled onto a higher priority project. They abandon the instance. What happens to that server over the next 6 months?
It falls completely off the map. It drops out of your automated patching cycles. Your vulnerability management scanners probably don't even know the subnet exists. It's just a silent door.
And as new vulnerabilities are discovered, as new CVEs for the Linux kernel or OpenSSL or Apache are publicly announced week after week, that abandoned VM slowly rots.
It does.
Becomes an incredibly soft target. And attackers know this. They have automated scanners relentlessly probing public cloud IP ranges, specifically looking for these forgotten, unpatched assets, because they know the Security Operations Center isn't monitoring the logs on a forgotten dev docs.
Let's ground this in reality by examining some of the most devastating cloud breaches in recent history from our research. We really have to look at the Capital One breach from 2019.
Oh, the big one.
It is legendary in cloud security circles, but we really need to dissect the exact anatomy of the attack chain because it is an absolute masterclass in how cloud misconfigurations and sprawl compound to create a catastrophic failure.
It really is the textbook example of a multi-stage cloud attack. The threat actor, who ironically was a former AWS software engineer and deeply understood cloud architecture, targeted an EC2 instance that Capital One was using to run an open-source web application firewall, or WAF.
Right, and the initial point of compromise was a vulnerability in that specific WAF configuration. The WAF was vulnerable to a server-side request forgery, or SSRF, attack.
Let's unpack the mechanics of SSRF for a moment, just so we're all on the same page regarding how devastating it is in a cloud context.
Good idea.
In a standard web application, an SSRF vulnerability allows an attacker to manipulate the server into making an HTTP request on the attacker's behalf. In an on-premise environment, you might use SSRF to probe internal network subnets or access administrative interfaces behind the firewall. But in AWS, SSRF is the holy grail for attackers.
It really is.
because it allows them to target the instance metadata service.
Exactly. In AWS, every EC2 instance can query a special internal IP address, 169.254.169.254. This is the IMDS, the instance metadata service.
Right.
It provides the instance with data about itself. But most importantly, if the instance has an INM role attached to it, the metadata service will serve up temporary security credentials, an access key ID, a secret access key, and a session token. So the software running on the instance can securely authenticate with other AWS services like S3 or DynamoDB.
So the attacker sends a carefully crafted HTTP JNT request to the public-facing WEF, exploiting the SSRF vulnerability. The wave, acting confused, takes the payload and makes a secondary request to that internal 169.254.169.254 metadata IP address on behalf of the attacker.
And the metadata service responds by handing over the temporary IAM credentials assigned to that EC2 instance.
Oh.
Now, this is where the blast radius expands from a single compromised server to a massive data breach. The IAM role that was attached to this WEF instance was massively, catastrophically overprivileged.
It had permissions to list and read the contents of almost every single S3 bucket in Capital One's massive AWS account. Why in the world would a web application firewall need administrative-level read access to petabytes of highly sensitive customer data buckets?
It wouldn't. Functionally, there is zero reason for a firewall to read back-end customer credit card applications.
So why was it there?
But this is the reality of cloud engineering under pressure. A developer or an architect probably couldn't get the WAF to write its logs to a specific bucket due to a complex IAM policy issue. So in frustration, they just applied a wildcard asterisk to the policy.
Oh, no.
Yeah, they gave it S3 to get object and S3 list bucket for all resources just to make the error messages go away and get the infrastructure deployed.
Just get wildcards so it works. It is the most dangerous phrase in cloud engineering.
Absolutely.
So the attacker uses the SSRF to trick the metadata service into handing over those temporary, highly privileged IAM credentials. Armed with those keys, the attacker simply configures their own local AWS CLI on their laptop, authenticates as the WARF role, and runs an Oz S3 sync command to quietly download over 100 million customer records from the S3 buckets.
It was a perfect storm of failures. The WAA was configured in logging mode instead of blocking mode. The SSRF vulnerability wasn't patched, the IAM policy was overly broad, and the S3 data access wasn't being proactively monitored for anomalous egress.
Unbelievable.
And this ties directly back to our discussion on Sprawl and Shadow IT. When you have thousands of instances across hundreds of accounts, ensuring that every single one has a tightly scoped, least privileged IAM role becomes an incredibly complex, almost impossible manual task. Sprawl hides these overprivileged time bombs.
And data theft isn't the only risk. Let's look at another massive incident from the research. The Tesla cryptojacking incident in 2018.
Oh, this is a weird one.
Very. This one is entirely different because the threat actors didn't care about stealing proprietary Tesla data or customer information. Their sole goal was stealing raw compute power.
It was a pure resource hijacking operation. Security researchers discovered that Tesla had an entirely open, unpassword-protected Kubernetes administration console exposed directly to the public internet.
An exposed K8's dashboard. That is basically handing over the keys to the kingdom.
It was an unmanaged shadow IT entry point. An attacker found this exposed dashboard. Once they were inside the Kubernetes cluster, they started digging through the configuration files and the containers, and they struck gold.
What did they find?
They found an AWS API key that a developer had lazily hard-coded directly into one of the container images.
Hard-coding AWS credentials into a Docker image or a GitHub repo is the cardinal sin of cloud development, but it happens every single day.
It does. And using those hard-coded AWS credentials, the attackers burrowed deeper into Tesla's cloud environment. But what makes this case study so interesting is how incredibly stealthy the attackers were.
How so?
They didn't just spin up 100 massive GPU instances and set off every billing alarm in the company.
Right. Because if your AWS bill spikes by $50,000 in a weekend, the FinOps team is going to shut you down immediately.
Exactly. These attackers were sophisticated, they spun up crypto mining instances, but they deliberately throttled the mining software. They kept the CPU utilization relatively low, perhaps hovering around 40 or 50%, to evade detection by standard billing alerts or high CPU CloudWatch alarms.
Sneaky.
They wanted to stay under the radar so they could mine cryptocurrency for as long as possible.
That is devious. They essentially blended their malicious compute usage into the background noise size of Tesla's massive, legitimate infrastructure footprint.
They went even further. They configured the mining pools to listen on non-standard network ports, and they routed all their command and control traffic through Cloudflare proxies to mask the true IP addresses of the mining pools. It highlights how sophisticated cloud attackers have become when exploiting sprawling infrastructure. They find one forgotten entry point, they extract one hard-coded secret, and they silently escalate their privileges to drain resources.
All of this brings up an incredibly important technical distinction in the research. We have to clearly separate the concept of VM sprawl from the concept of VM escape, because while they sound similar, they represent entirely different threat vectors.
It's a critical distinction for a security architect to make. VM sprawl, which we have been dissecting, is the unchecked proliferation of virtual machines. It is a failure of governance, lifecycle management, and architecture. It provides the environment for an attack.
Okay, and VM escape?
VM escape, however, is a severe, highly specific technical vulnerability at the virtualization layer.
VM escape is the absolute nightmare scenario for any cloud provider. It's a vulnerability where an attacker successfully compromises a guest operating system on a virtual machine and then exploits a flaw in the hypervisor code to break out of that isolated guest environment and execute code on the underlying physical host itself.
Whether that hypervisor is VMware ESX, Microsoft Hyper-V, or KVM, if an attacker achieves a VM escape, the isolation model of the cloud completely shatters.
Because they own the box now.
Exactly. The attacker now controls the host hardware. From that vantage point, they potentially have access to the memory space and the disk I/O of every other virtual machine running on that physical server, even if those VMs belong to different customers or different security domains.
So how do these two concepts connect? Why are we discussing hypervisor 0 days in a deep dive about sprawl?
Because sprawl massively increases the statistical surface area for a VM escape to occur. A VM escape requires an initial foothold. The attacker has to compromise a guest VM first.
Ah, I see.
When your environment suffers from massive sprawl, resulting in hundreds of unpatched, unmonitored zombie servers, you are providing attackers with hundreds of soft targets. They only need to compromise one forgotten dev server to secure the staging ground they need to attempt a complex hypervisor breakout. By eliminating the sprawl, you eliminate the staging grounds.
Now, I know there's a cloud architect listening to this right now who is thinking, hold on, doesn't my cloud provider handle this? Doesn't AWS secure the underlying EC2 infrastructure? Doesn't Azure secure the hypervisor? What about the shared responsibility model? I'm paying them to worry about this.
The shared responsibility model is arguably the most misunderstood, misquoted concept in the entire cloud computing ecosystem. People assume it's a blanket insurance policy.
Let's ground the shared responsibility model in a real-world analogy. It is exactly like renting a luxury apartment in a high-security, high-rise building.
Okay, I like this.
The cloud service provider, AWS, Azure, Google, they are the building management company. They're responsible for securing the concrete foundation, maintaining the elevators, employing the physical security guards in the lobby, and ensuring the locks on the main front door of the building cannot be picked.
In cloud terms, that is the security of the cloud. The data centers, the physical networks, the hypervisor patching.
Exactly. But you, the enterprise tenant, are responsible for what happens inside your specific apartment unit. If you decide to leave your apartment door wide open, place all your expensive jewelry and laptops on a table pointing toward the hallway, and then go on a 2-week vacation, the building management is not going to stop someone from walking down the hall, entering your apartment, and taking your stuff.
That's on you.
That is security in the cloud.
Yeah.
You are entirely responsible for your IMM roles, your network firewall rules, your guest operating system patching, and your data encryption.
Right. If you use the API to spin up 1,000 virtual machines, open port 22 to the entire public internet, and leave them running unpatched for 2 years, Amazon is going to happily keep sending you a bill every month while the attackers have an absolute field day inside your network.
If you are listening to this right now, I want you to pause and internalize that. When you get back to your desk, or when you open your laptop tomorrow morning, look your own IMRLs.
Highly recommend it.
Look at the policies attached to your legacy applications or old service accounts. How many of them have wildcards, the asterisk symbol in their S3 access policies, simply because it was easier for an engineer to deploy it that way 3 years ago?
It's a sobering realization because threat actors do not care if a cloud asset is currently active, if it has been marked as obsolete, or if it has been entirely forgotten by your IT department. They only care if it is exploitable.
Which brings us to the operational reality of fixing this. We have established the financial hemorrhage. We have established the terrifying security risks. The question for the security practitioner is, how do you actually find these hidden risks in a massive, chaotic, multi-cloud environment?
It's like finding a needle in a haystack.
How do we build diagnostic frameworks to shine a light on shadow IT?
Shadow IT is the crux of the diagnostic problem. When we say shadow IT, we are talking about resources that are spun up without central stakeholder oversight, entirely outside of corporate policy, usually via decentralized ad hoc decision-making by individual engineering teams who are just trying to move fast.
And the research highlights the recent Oracle security incident as a stark reminder of the dangers of shadow IT and legacy infrastructure.
Right. When Oracle suffered a breach, they were quick to clarify that their modern, current-generation cloud architecture wasn't compromised. The breach actually affected a legacy system, an older piece of infrastructure that was still lingering online.
It perfectly exposes the hidden danger of forgotten environments. An IT department might formally label a system as decommissioned or obsolete in their internal documentation. But if that server is still physically running and it is still accessible from the internet, it is a prime target.
Attackers aren't reading your internal Confluence pages, they are scanning IP ranges.
Exactly. So how do we systematically find these zombies? You have to start with detection methods. The baseline approach is utilizing the native tools provided by the cloud vendors: AWS Cost Explorer, Azure Advisor, GCP Recommender.
These native tools are a great starting point for establishing a baseline, right? They analyze your historical usage patterns and spit out recommendations.
They are decent for surface-level visibility. They can help you identify instances with extremely low CPU utilization. The standard metric that these tools look for is a virtual machine with less than 5% average CPU utilization, coupled with minimal network input-output for 30 consecutive days.
Mathematically, if a machine hasn't computed anything significant and hasn't transmitted any data over the network in a full month, it's highly probable that it is a zombie.
But here is where the diagnostic frameworks get really interesting, and where relying solely on native tools often leads to failure. Native tools provide visibility, but they almost entirely lack automated enforcement and contextual governance mechanisms.
To go back to an analogy, relying purely on native cost tools is like installing a basic smoke detector in your house. When a fire starts, the smoke detector will loudly and aggressively tell you that there is a fire.
Beep, beep, beep.
Right, but you still have to wake up, get out of bed, walk to the kitchen, find the fire extinguisher, and put the fire out yourself. The tool won't automatically extinguish the flames.
And that lack of automation leads directly to a massive psychological barrier in security operations: alert fatigue.
Oh, alert fatigue is brutal.
Imagine being a level 1 SOC analyst or a FinOps analyst. You log into your centralized dashboard on a Monday morning, and your native cloud tool has flagged 5,000 idle resources scattered across 40 different AWS accounts.
You are immediately hopelessly overwhelmed. A human being cannot manually investigate, trace the ownership of, and safely decommission 5,000 individual alerts. The cognitive load is too high.
So what does the analyst do?
They acknowledge the alert, close the dashboard, and ignore the problem. This is exactly why we need prioritized, context-aware diagnostics instead of just raw data dumps.
Wait, I want to push back on the 5% metric we just discussed. You said that a VM with less than 5% average CPU for 30 days is highly probable to be a zombie. But what if it isn't?
What do you mean?
What if I have a disaster recovery database node sitting in a secondary AWS region? It is architecturally designed to sit at 0% CPU for months at a time, just waiting for the primary data center to get taken offline by a ransomware attack or a natural disaster.
Right.
Or what if it's a highly specialized, low-traffic security appliance, like a Bastion host or a jump box that only gets accessed by an administrator once a quarter? If a script blindly deletes everything under 5% CPU, you've just destroyed our incident response architecture.
That is the exact scenario that keeps infrastructure managers awake at night, and it highlights why context is the absolute foundation of diagnostics. You cannot blindly script a Python tool to terminate every low CPU server.
What's the fix?
This is where metadata and tagging become the lifeblood of your cloud environment. If that disaster recovery node is properly tagged with key value pairs like environment, disaster recovery, and criticality, Tier 1, your diagnostic tool has the context it needs to exclude that specific instance from the zombie termination list.
Context is king. But let's say we have the context. We filtered out the DR nodes, the Bastion hosts, and the seasonal workloads. We are left with a definitive, highly accurate list of 500 absolute garbage zombie VMs that are wasting money and creating risk.
Okay.
Manual cleanup is still not the answer. You can't ask an engineer to log into the console and click terminate 500 times.
Manual cleanup is a guaranteed failure path. It doesn't scale, it is prone to human error, and it doesn't solve the ongoing nature of the problem.
Which brings us to the operational solution: technical remediation and automated decommissioning. If manual effort doesn't scale, automation is the only answer. We have to transition from passively finding the problem to systematically destroying the problem using code.
We have to build an automated remediation pipeline. And the research outlines a beautiful, elegant architectural pattern for this: the AWS serverless cleanup loop. It is a masterclass in event-driven architecture.
Let's unpack the serverless cleanup loop step by step, because this is the exact blueprint a cloud security team can take and implement tomorrow.
The pipeline starts with Amazon EventBridge. For those who used AWS years ago, this is the evolution of CloudWatch events. We use EventBridge as a highly reliable serverless cron job. We configure a rule to trigger at, say, 2 a.m. every single night.
So EventBridge acts as the trigger. It fires an event that invokes an AWS Lambda function. Lambda is our serverless compute service. We just write the Python code, and AWS handles the underlying execution environment.
Exactly. The Lambda function wakes up and assumes an IAM execution role that grants it specific read and write permissions across the AWS environment. The first thing the Python code does is execute an API call using the Boto3 library. Describe instances.
Okay.
It asks the AWS API, give me a complete paginated list of every single EC2 instance currently running in this region.
Once the Lambda has that massive list of instances, it has to filter. It looks at the metadata dictionary for each instance. It filters specifically for instances carrying tags like environment, dev, or environment, sandbox. Or even more aggressively, it filters for instances that are completely missing mandatory ownership tags.
Now, the Lambda has a suspect list. For every instance on that suspect list, the Lambda function makes a secondary API call to Amazon CloudWatch. It queries the historical metrics, specifically asking for the CPU utilization over the last 7 to 14 days.
Makes sense.
But it doesn't look at the average CPU. Average CPU is a deeply flawed metric because a server could sit at 0% for 6 days and then spike to 100% for 1 day.
Oh, that's true.
Instead, it looks at the P95 or P99 metrics, the 95th or 99th percentile of utilization. If the P99 CPU metric is under 2%, we know with near certainty that the machine is not doing any meaningful work.
So the Lambda function has identified a definitive zombie. But it doesn't just ruthlessly kill the server right then and there. That would cause chaos.
Right, we need a safety buffer. The Lambda function publishes a message to an Amazon SNS topic simple notification service. This triggers an automated email or a Slack webhook directed to the team that owns the instance tag. Exactly. The message essentially says, we have identified instance I123456 as idle. It has been scheduled for automated termination in 24 hours unless you intervene.
It provides a 24-hour grace period. It puts the burden of action on the developer. And if the developer ignores the email or if no one clicks the Save My Server link to exempt the instance,
the state is tracked, perhaps in a lightweight DynamoDB table. The next night, the Lambda function runs again, checks the DynamoDB table, sees that the 24-hour grace period has expired without intervention, and executes a terminate instances API command.
Damn.
The instance is destroyed, the attached volumes are deleted, and the zombie is permanently dead.
It's an incredibly elegant system. Think of the Lambda cleanup loop as a digital Roomba.
Yeah.
You program the boundaries, you set it on a nightly schedule, and it just endlessly, tirelessly patrols the hallways of your cloud environment. It bumps into instances, checks their metrics, sweeps up the unused resources, and keeps the floor completely clean without human intervention.
A digital Roomba is the perfect way to visualize it, and we can apply a similar automated approach to dormant servers using a standard operating procedure, or SOP.
Let's talk about the dormant server decommissioning SOP, because shutting off a server is one thing, but dealing with the data is another.
Consider a virtual machine that a developer manually put into a stopped state. It has been stopped for 90 days. Because it's stopped, it isn't racking up hourly compute charges, so it flies under the radar.
Right.
But it is still holding on to expensive, provisioned EBS storage volumes. The automation script identifies this 90-day dormant VM, but instead of just ruthlessly deleting the underlying volumes, the script executes a safety protocol. It triggers a final snapshot of the entire VM and all attached storage.
It creates a safety net before destruction.
Exactly. It verifies the snapshot is complete, and then it completely deletes the underlying VM and the EBS volumes, instantly stopping the billing meter. But, and this is the critical part, it retains that snapshot in S3 for 180 days before final permanent deletion.
I really want to focus on that 180-day snapshot rule, because from a pure engineering perspective, it seems like unnecessary overhead. Why pay to store a snapshot of a garbage server for 6 months? But from an organizational and psychological perspective, it is a masterstroke.
It's fascinating because it directly solves the human behavioral problem of IT hoarding.
Application owners and developers are notorious hoarders. They suffer from intense separation anxiety regarding their code and their infrastructure.
Oh, they definitely do.
If you approach an application owner and say, hey, your dev server hasn't been used in 3 months, we're going to delete it, they will inevitably fight you tooth and nail. They will say, no, don't touch it. We might need to reference that configuration. We might need to look at those logs for the upcoming Q3 release.
But if you change the narrative and approach them by saying, we are deleting the live server to save budget, but we are taking a full snapshot and keeping it for 6 months. If you ever realize you need it, submit a ticket, and we can resurrect the exact server in 5 minutes. The anxiety evaporates.
It completely appeases them. It provides a guaranteed, no questions asked rollback path. And by providing that psychological safety net, you entirely remove the political friction of deleting resources. You get to clean up the environment, you close the security vulnerabilities, finance is happy with the cost savings, and the application owner feels secure.
Win-win.
And the best part, in 99.9% of cases, the developer never actually asks for that snapshot to be restored. 6 months pass, the automation permanently deletes the snapshot, and no one even notices it's gone.
It is brilliant engineering psychology applied to infrastructure management. And we have to apply these same automated lifecycle concepts to our raw object storage as well.
Absolutely. S3 lifecycle policies are non-negotiable. You configure rules at the bucket level. Raw application logs are written to S3 standard. After 7 days, when they are no longer needed for immediate operational troubleshooting, a lifecycle rule automatically transitions them to S3 standard infrequent access, cutting the cost in half. Backups and database dumps older than 90 days are automatically transitioned to Glacier Deep Archive, or scheduled for permanent deletion. The automation prevents future storage zombies from ever forming.
So automation acts as our highly efficient firefighter, constantly putting out the small fires of Sprawl before they burn the house down. But how do we stop the arson?
All right.
How do we prevent the engineering teams from creating these chaotic messes in the first place? That requires a shift from reactive automation to proactive strategy. We have to discuss strategic governance and FinOps culture.
Automation is reactive, governance is proactive. The absolute bedrock of proactive cloud governance is policy-driven tagging.
We talked earlier about how missing tags paralyze the cleanup effort.
Yeah.
But how do you actually force an organization of 500 developers to consistently tag their resources? Because I can promise you, if you just send a polite email from IT asking everyone to please remember to tag their instances, it will be ignored immediately.
You cannot rely on human compliance. You have to enforce tagging at the point of creation, mechanically, via infrastructure as code or IAC. Whether your teams are deploying via Terraform, AWS CloudFormation, or Pulumi, you build governance policies, perhaps using Open Policy Agent or HashiCorp Sentinel, that literally reject the deployment pipeline if mandatory tags are missing.
It acts as a hard block at the commit stage.
Yes. You mandate that every single Terraform module must accept an owner tag, an application tag, and an environment tag. If a developer tries to execute a Terraform apply without defining those variables, the CI/CD pipeline fails, and the infrastructure is never built.
Strict but necessary.
And if a developer tries to be clever, bypasses the pipeline, logs directly into the AWS console, and manually clicks around to create an untagged EC2 instance. A continuous compliance tool like Cloud Custodian detects the untagged resource within minutes and either flags it for immediate remediation or simply auto-deletes it on the spot.
Another incredibly powerful proactive governance tool is the enforcement of time to live, or TTL policies.
These are especially critical for non-production workloads. When a developer needs a sandbox environment to test a new database schema or a QA environment to run an integration test, they shouldn't just provision it open-endedly. They should be forced to select a TTL during the provisioning process, 24 hours, 3 days, or 1 week. When that timer expires, the entire environment automatically self-destructs.
It forces hygiene by default. And of course, we must enforce role-based access control, or RBAC. We have to strictly govern who possesses the IAM permissions to provision specific classes of infrastructure.
Least privilege.
Exactly. We must enforce the principle of least privilege. A junior developer spinning up a test container doesn't need and shouldn't have the IAM permissions required to deploy a fleet of massive, expensive P4D GPU instances.
Let's take that a step further, into the realm of architectural efficiency. Because governance isn't just about blocking bad deployments. It's about guiding engineers to design better, more cost-effective systems.
A perfect example of architectural efficiency is managing network egress costs. Suppose a data engineering team deploys a massive Apache Spark analytics cluster in AWS Availability Zone A.
Okay.
But the multi-petabyte S3 bucket holding the raw data is located in Availability Zone B. Every time that cluster pulls data to process it, the data crosses the AZ boundary, and the company gets hit with massive cross-AZ data transfer taxes.
Ouch.
Proactive governance means establishing architectural review boards or automated linters that teach and enforce the co-location of compute and storage in the same AZ.
Or moving away from static provisioning entirely by leveraging horizontal pod autoscaling, or HPA, in Kubernetes.
Exactly. Instead of an architect looking at a microservice and statically provisioning a fixed cluster of 20 nodes just in case of a massive Black Friday traffic spike, you teach them to design dynamically.
Makes a lot of sense.
You establish a baseline of 3 nodes, and you configure HPA to monitor the actual CPU utilization or the incoming HTTP request queues. As the traffic spikes, Kubernetes dynamically spins up new pods to handle the load. When the traffic subsides, it gracefully scales the infrastructure back down to the baseline. You scale with real demand rather than paying for theoretical capacity.
All of these technical policies, the tagging pipelines, the TTLs, the autoscaling, they drive a fundamental cultural shift within the organization. Historically, the security and finance departments have been viewed by engineering as the department of no. They were the roadblocks to innovation.
And changing that perception is the true cultural objective of FinOps. A mature FinOps practice isn't there to stop engineers from building. They're there to empower engineers with visibility. They implement the tooling, they build the Grafana dashboards, and they create the feedback loops so that a developer can instantly trace the exact financial and security impact of their architectural decisions in near real time.
When a software engineer writes a highly inefficient database query, and they can look at a dashboard the next morning and see that their specific block of code isn't just executing slowly, but is actually costing the company an additional $2,000 a week in compute time, it fundamentally changes their behavior. It transforms an abstract concept into a tangible engineering metric.
It creates a culture of accountability at the edge, right where the decisions are actually being made.
I want to turn this back to you, the listener, for a moment of reflection. Think about the engineering culture in your own organization. Are your developers and cloud architects building infrastructure with cost parameters and security controls baked directly into their infrastructure as code modules from day one? Or is security strictly an afterthought?
That's the real question.
Is your security team constantly scrambling to bolt IAM policies and network firewalls onto applications right before they go live in production?
Because if security and governance are treated as an afterthought, if they are just checkboxes on a pre-flight checklist, you are structurally guaranteed to suffer from massive, continuous sprawl.
Let's bring all these threads together. What we've uncovered in this deep dive today is that cloud VM sprawl is not merely an IT housekeeping issue. It's not just about having a messy digital garage. It is a critical, volatile intersection of massive financial risk and severe, exploitable security vulnerabilities.
It's the ultimate blind spot. It silently drains your operational budget while simultaneously leaving your doors unlocked for attackers.
Before we wrap up this deep dive, I want to leave you with a final provocative thought to consider. Everything we have discussed today revolves around human engineers making mistakes, humans forgetting to tag an instance, humans over-provisioning out of fear, humans hard-coding API keys. But look at the horizon. Think about the explosive rise of artificial intelligence and autonomous agents.
Oh, yeah.
How will AI-driven cloud provisioning impact the sprawl equation? Imagine a future, perhaps only months away, where autonomous AI agents are granted the IAM permissions to dynamically spin up their own cloud infrastructure to process massive datasets or train models. If these AI agents can provision resources at machine speed, the velocity of sprawl could increase exponentially, entirely bypassing human oversight.
It introduces the concept of machine speed sprawl. If a human engineer can create a chaotic, sprawling mess with a few clicks over a few months, imagine what a runaway AI agent could do if it encounters a logic error and provisions 10,000 virtual machines in 60 seconds.
How will your current human-centric governance policies handle non-human identities provisioning infrastructure at algorithmic speeds? Will your native CAS tools catch it before the bill hits millions of dollars? It is a paradigm shift that cloud security architects desperately need to start planning for right now. We will need autonomous AI security agents just to police the AI provisioning agents.
That is a fascinating, terrifying rabbit hole, and definitely a topic for a future discussion.
Thanks for tuning in to InfoSec Bytes. Keep exploring our 100-plus episodes on information security, AI, cloud, quantum, and cybersecurity, incident root cause analysis. Please like, subscribe. We are on various platforms: Spotify, Apple Podcasts, YouTube, Amazon Music, and share to stay connected and keep your cyber defenses strong. See you in the next episode. Stay tuned.
Before you close your laptop or finish your commute today, I want to challenge you. Run a quick query in your primary cloud account. Find just one orphaned snapshot or one untagged development instance that has been running quietly since last year. Trace it back. See who built it, why it was abandoned, and how deep the rabbit hole goes. Stay secure.